Hey guys, in this video we're going to do a couple of examples of questions dealing with rotation, mostly rotational kinematics. And I'll start with a brief introduction of some of the terms that we're going to use in rotation in case you were absent or you need some reminders. Okay, so first thing, whenever we're talking about rotational quantities like angular acceleration or angular velocity or angular displacement, all of these things are analogs, meaning analogous to other things that you already learned about in linear motion, like linear acceleration and angular acceleration are analogous to each other. And a linear acceleration causes a change in linear speed, whereas an angular acceleration is going to cause a change in rotational speed. Okay, and so other than that, there's not really all that much of a difference, right? One is analogous to the other, and if you need to pause the video right here and write down units or copy down this chart, that'd be a great idea, particularly if you are absent. Okay, now, what that means is all of the equations that you learned back in 1D kinematics have a rotational analog as well. Basically, if you take V equals V naught plus AT and you sub in instead of V, omega, all right, V naught, omega naught, and A is going to be alpha, then you have an equation that applies to a rotational system instead of a system that's just undergoing change in its linear motion. Okay, so all of the kinematics equations just slide right on over into the rotational world. You just change out the letters for the ones that you actually need. All right, the other key concept. Linear and angular quantities are often related. For example, if you're driving a car along down the road, right here you go down the road, your tires are also spinning while your car moves forward. Okay? The relationship between those things is always going to be given by V equals omega R. Meaning, if your car is rolling30 at, let's say, 20 meters per second, and the radius of your tires happens to be, let's say, 35 centimeters. That's probably more reasonable. Let me pick some easier numbers. How about your speed is, we're not going too fast here, how about 3.5 meters per second? That's definitely within the speed limit. All right, equals, and if the radius of your tires were 35 centimeters, that's 0.35 meters. That would give you an angular velocity of 10 radians per second for your tires. Okay, so whenever you need to convert between one or the other because you're talking about a rolling tire or, another example, objects on a spinning wheel, V equals omega R is going to be your friend, right? So if you want to relate the speed of this to the angular velocity of this, it's going to be V equals omega R. Okay, and so the object that's closer to the center then is going to have a smaller speed, smaller linear speed, than the object that's on the outside edge, because the one on the outside edge has to go through basically twice the distance because the circumference of the circle that it's going through is quite a bit larger. Okay, now, the new stuff. If you were in class, you already kind of worked through the first two parts of this on the board. If you were not in class, then you obviously missed it. But what I'm going to do is sort of start at the beginning with them. Okay, and then even if you were in class, maybe you didn't write it down because you just did it on the boards or something. And so it's going to be productive for you to take notes on this as well. All right, all three of these questions, sorry, I'm erasing to make room here. Okay, all three of these questions are going to have to do with the relationship between linear quantities and angular quantities. So in the first question, it's asking about the angular speed of a car's tires, assuming that the car is traveling at 40 kilometers per hour. Okay, and we want the answer to be in radians per second. If you need to read the question, pause the video. Okay. So to begin with, 40 kilometers per hour is not okay as a unit, right? We need to turn that into meters per second. So if you want to turn that into meters per second, 40 kilometers per hour. We'll multiply by 1,000 meters per kilometer, and then divide by 3,600 seconds in 1 hour, right? 60 times 60. Okay, so all told, our speed here, the speed of the car is going to be 11.11 meters per second. Okay, so that's how fast the car is going, is 11.11 meters per second. Let's see if we can do something about that glare. Nope, can't fix the glare. Okay, so 11.11 meters per second. All right, so the question then was, what is the angular speed of the tires if that's the linear speed? The equation we're going to use for that is V equals omega r, where r is going to be the radius of the tires. All right, so if the tires are rolling along at 11.11 meters per second, using a radius of 35 centimeters, which I didn't just entirely make up, right? I got that off of the internet more or less, or you could go out and measure your tires. Most tires are around like 28 inches across, which means they're 70 centimeters across more or less, which gives you a radius of 0.35 meters. Okay, that's going to give us an angular velocity for our tires of some number. This is the part where I wish I could pause recording, but I don't. All right, 31.74 radians per second. Okay. Now, the next question. How many revolutions does a tire go through crossing the Rockhurst High School parking lot? Now, if you were here in class, I made you actually kind of figure out how far it is across the parking lot. We're just going to use 50 meters and go with it. If it's 50 meters across the parking lot, that means that the displacement that you're going to have to go through is going to be 50 meters. But what does that have to do with the number of revolutions and like what is a revolution? All right, when we're talking about revolutions, one revolution is one time around a circle, which is going to be 2 pi radians. Okay, so we should be able to turn this displacement into an angular displacement, which is going to be based on the radius of our tires. And then we should be able to turn that angular displacement in radians into revolutions. We said that V equals omega r was an equation you were going to use all the time, but all of the angular quantities work the same way as V equals omega r. If you want to relate linear and angular acceleration to each other, it's the same relationship. If you take an angular quantity times the radius, then you get the corresponding linear quantity. All right, so that means that if I want the number of revolutions, I should be able to say delta x equals delta theta times r. All right, and then using again my radius of 0.35, we'll get that the angular displacement that our tires go through crossing the parking lot is, drum roll, 142.86 radians. All right, now that wasn't the question that was exactly asked, right? It said how many revolutions, so that means that we need to divide by the number of radians in revolution, which is, you should be thinking right now, 2 pi. So we'll divide by 2 pi. So we get 22.74 revolutions. Okay, so your tires would have to go around 22 3/4 times in order for you to cross the parking lot using these main numbers. Okay, Part C now. The number of revolutions your tire would have to go through if your car goes from 0 to 100 kilometers per hour in 15 seconds. All right, well, let's make some room for myself here. First, let's deal with the kinematic side of things, right? The information you have is an initial velocity, a final velocity, and the time. Okay, so that's going to be enough information for you to do something like come up with a horizontal displacement that your car would have to go through, or an acceleration if that's exactly what you want to get. So, all right, so let's think about what we're going to be able to get from this information. You have a V naught, a V final, which is unfortunately in kilometers per hour, and a time. If we want to know revolutions, that's an angular displacement, and that's related to a linear displacement. So we would like to know delta x so that we can get delta theta. Unfortunately, there's no equation that has these things and delta x in it. So that means that we're going to have to actually find acceleration first and then go from there to the delta x. All right? So that points us towards equation number 1, v equals v naught plus at. 100 kilometers per hour, if we turn that into meters per second, all right, it's going to be 27.78 meters per second. All right, whoops, t equals 15. All right, so that's going to give us an acceleration of, whoops, all right, an acceleration of 1.85 meters per second squared. Okay, so some good old 1D kinematics here. Now, from there, we said since we want revolutions, where we're going to need to go from there is what is the linear displacement. All right, so that means I need to use some other equation. At this point, it's totally your choice which one you want to use, this one or whatever. We have enough information, you could use either one. So if I pick this one here, 27.77 squared divided by 2 divided by 1.85. All right, gives us a displacement of 208 meters. Okay, so if that didn't make sense to you, all I was doing was plugging in my final velocity, initial velocity, the acceleration I found up here, and then the only thing I don't know is delta x. All right, and we set a displacement of 208 meters, approximately. All right, so then the number of revolutions. We said way over here that delta theta, or no, I guess I erased it. Delta x equals delta theta times r. The radius of our tire that we are still using is 35 centimeters. Which means that the number of radians that our tire would go through would be 595.5. All right, radians. And dividing that by 2 pi, we should get 94.78